Hello everyone. This presentation is in the framework of deliverable number 5 of work package 3 InnoDC project, and the topic is the interactions classification in a voltage source converter based high voltage direct current system. Within this presentation, I'm going to cover a very rough classification about the possible interactions in an HVDC link, and then it would be followed by a case study. Many studies have been revealed that there is quite strong interactions in an HVDC link. An HVDC link comprises a voltage source converter on the receiving end and on the sending end, and there is a DC transmission system in between, which is usually DC cable. This HVDC link is connected to two AC grids on either sides, and there is a strong interactions between AC grid and the control system of voltage source converter. Also, there is interaction inside the HVDC link between the control system of these two voltage source converters. The AC grid on the either side can have a significant impact, as the voltage of these AC grids would have some disturbances. These disturbances can degrade the control system of these two voltage source converters. The reason we need to classify the interactions in an HVDC link is to find what is the nature of many problems in the system. In any kind of systems, including an HVDC link, there are some specific critical modes with a very low damping that if goes unattended, they may lead to instability. So with interaction analysis, we can find what parameters are actually interacting with each other and giving rise to the critical modes of the system. The next step is to utilize utilize the understanding of these interactions in the control system design. A control system designer needs to have a knowledge about the interaction. So when the designer is trying to find the optimal PI controller from a specific input to the output, the designer needs to know what is the largest transient on the output and from which input actually. And this is kind of interactions. Any control systems have many inputs, including its reference and other disturbances, and all of these inputs have impact on the outputs, but which one is the biggest? This is the question to be answered. And then based upon this knowledge, we can tune our control system better to avoid increasing the interactions between control loops. There are quite a couple of approaches that it's called loop decoupling to reduce the interactions and so on. So here we try to provide a very rough classification of interactions we can the interactions may happen in an HVDC system. In order to quantify interactions, we need a model of the system, and any systems, at least electrical engineering system, can be modeled via state space equations. The linear model has states which are in the state vectors or x, and there are quite different interactions. Some interactions can happen here only between state variables. We don't need the knowledge of B, C, and D and the outputs. It is totally regardless of the outputs, and it happens between the state variables of the system, which are in the state vectors. The only thing we need is the matrix A to see how the state variables are interacting. Another class is the input-output interactions, that we select a specific input and output, and from the desired input to the desired output, we are interested to see how it is coupled from this input to the specific output. This coupling impact, and we find, is based on the input and output. So we will have two broad classification. One is called the state variable interactions, which only relies on matrix A of system. And the next one is input-output interaction, which actually depends on the choice of input and output. It depends on the decision of the design engineer. If the engineer wants to have a specific, for example, if the engineer wants to design the DC voltage, and the engineer would find what are the inputs as disturbance, what is the reference to the system, and the output is the DC voltage, and the engineer can see how the output and inputs are coupled and which one of the inputs have the large impact on the specific outputs. So it is the matter of design, the second group of the interactions. And we do need all the system matrices to analyze this interaction. In this chart, we try to make it more clear that interactions could be in category 1, state variable interaction, or input-output interaction. Input-output interaction can be further divided into 3 types. The types are only to emphasize that these are different, and the reason we are using them are different. So it is single input, single output analysis, multi-input, single output, and at the end, type 3, multi-input, multi-output. With the state variable analysis, what we are looking for is the state variables giving rise to the critical modes of the system. With the input-output, it is the control engineer. With type 1, we are checking one by one input-output to see which one has the largest transient on the output. And the typical tools for this is border plot and normalized input participation. Actually, this normalized input participation is an extension to the border plot, but it is just like another representation of the results of the border plot. With type 2, it is useful for the control system design. We want to see, for example, how DC voltage is coupled with the active power control loop. And this information is useful to see if I have a strong coupling between 2 variables, 2 control loops, then I need to take measures to reduce that interactions. Or in a positive side is that if the interaction is high, then I can make a feed forward between these 2 control loops and contract the deteriorating dynamics of these variables with different approaches. One of them is loop decoupling. The other one is the concept of feed forward to decouple the dynamics. Type 3 is a little bit conceptual, that if you consider all inputs to your design, what combinations of all inputs can be the worst combination. For example, if you have your AC voltage is dropped by 10%, if your active power has a step of 20% increase, all these what combination of all these elements of the inputs can lead to the worst transient on the output vector, and all of the outputs. It's a vector of outputs. So it is all in all situation, all inputs and all outputs. To better illustrate if this classification is useful or not, or why we're using them in first place, let's have a case study on a modular multi-level based HVDC system. Here VSC 1 and VSC 2, as indicated by C, is a MMC. This is transformer, the model of transformer, which is RL circuit. The grid has a Thevenin equivalent system, both of them, and the DC transmission system is a model of the DC cable. Writing state space equations of all these elements and connecting them together based on the input outputs, we can find an overall linear model of the system. The system, it could be a state space equation or transfer function, whatever. The inputs are selected based on the importance of the variables. For example, these are the main control references for the MMC1 here. These are the main controller references for MMC number 2. AC grid 1 and AC grid 2, we took the voltage only as the main disturbance of the grid. In this study, we are considering that the AC grid is quite strong. The short circuit level is around 10. So we are quite sure about the frequency. So we are only concerned about the voltage fluctuation here, or because anyway you will have some step changes on the AC grid voltage here and there, and your DQ axis. On the output, we choose these 4 variables, 2 from MMC1 and 2 from MMC2, because we observe that the dynamics of these 4 variables are dominant in an HVDC link. There are also in-ear current control loops. They have also references. They are also controlled variable. But because they are very fast, they are usually the bandwidth is like 1000 radian per second, and they are very fast control system. Maybe 1 millisecond is the time constant of the loop. So they are pretty fast and they can follow the reference quickly. But the references here, because of the cascaded control system basic rule, they should be 10 times at least slower. So they are quite they are 10 times slower than the in-ear loops. So their dynamic it could be more important in the system, more influential. But also notice that here is the control variable and here is the reference for this control system. Here again, and the reactive power, this is the DC voltage, total stored energy, because this MMC, this is the reactive power, but in our model we didn't include any PI controller for reactive power, and it is based on reference calculation. So reactive power based on the reference is only used to calculate the current, the reactive component of the grid current. Active power of MMC2 and the total energy again, and the reactive power, and these are the grids. first, let's take a look at the state variables interaction as the first category. We are using eigenvalue analysis and participation factor, and here A and B are the critical modes of the system. 10 modes are here and 2 modes are here. These are very high frequency modes, and they are excited. By the state variable, we can see that the capacitor voltage and inductor currents of the DC cable model, they interact with each other, and they are causing some resonance frequency, and it is very low damped frequency. This is damping ratio, and it is maybe less than 10% easily. And the second category is related to the many parameters are contributing to this low frequency, to this low damping mode again. The other modes are pretty well damped, but these two also have maybe less than 30% damping. And if we want to see what interactions between which state variables are giving rise to these two modes, they are low frequency also. It is DC voltage PI controller, circulating or additive current of MMC1, circulating current of AC grid 1, and the total stored energy of MMC1. All of these parameters, all of them are state variables, and all of them are with different percentage. They contribute differently, but all of them are important. I mean, they work together, and as a result, these two low frequency modes are excited. With regard to input-output interactions, type 1, the main reason we are looking into this kind of interaction is to find what is the biggest input in terms of the largest amplification on the specific output. For this, we are plotting the Bode plot of this system, and for this specific output, for example, as it is clear here, the total energy 1 and total energy 2, these are reference values, these are inputs. So, for example, as a control engineer, it is interesting for me to know that for frequency, which is around 300 radian per second, which is not very high, 300 radian per second. For this low frequency, I mean, at least it is near fundamental frequency, I expect that if energy 1 and energy 2 has some change, maybe if something is happening in MMC and total energy goes through some transient, I expect to see that on the DC voltage too. So, but on the other hand, the grid voltage, they have lower impact. This kind of analysis could be done for all four variables. However, for active power, it is not very influenced by the system inputs. It is. And the reason is the decoupling inside the MMC with the feed forward. Here also it is observable that there is a frequency band here around 300 radian per second, that the other inputs of the system are becoming important. For example, here for low frequency, it is only the reference for the DC voltage, which is normal, that the reference has the largest impact. But as we pass through 300 frequency, the reference is not the most influential parameter to the output. So we can find is the largest which input can cause the largest input on this transient on the output. At each frequency, we can have such graph. It is normalized input participation. So, for example, this is at frequency of around 350, 370 radian per second, and For example, on the DC voltage, it is observable that, as we already observed in the Bode plot, that these two, total energy of 1 and 2, for example, total 1 has more than 80% amplification on the output. And this is the reference for DC voltage, and it is not much. For every frequency of interest, it depends on our system. If we find specific critical frequency, we can conduct this analysis on that frequency to see for these 4 control loop, which input has a major impact. In general, the total stored energy of MMC1 and 2, they are very influential on the 3 control loops. On the power, they are not very influential. This is the grid voltage has more impact, but only at that specific frequency. So once we find the largest disturbance on the output, we can move to a more complicated topic, which is the interactions, which is mutual interactions normally between two or several control loops. Here we have the references of the control loops, and here are the outputs of the control loops. From all the references, there is a coupling impact on each individual control loops. So we can realize that what is the coupling between these control loops. And the suggested tools is frequency-dependent RGA analysis. And as it is plotted here, this relative gain array analysis suggests that around the frequency band 300 to 400 radian per second, all the control loops start to interact between each other, except the power loop. Power loop is kind of decoupled from the system. So these are nice results. So a designer would be less worried about the active power loop. So the designer can focus on the DC voltage and total energies. This is the reference for the DC voltage, for example. Until 100 radian per second, the control loop is only influenced by its reference. But when we move to frequency band of 300 to 400, then reference is not the only one. So the impact on the output of DC voltage would be again by the total energy of 1 and 2. And so a designer may think at this moment that if the total energy of 1 and DC voltage of both of them are inside MMC1, so if they are coupled so much, so why not to find a cross link between them, or feed forward energy to DC voltage and DC voltage to energy, and improve the overall dynamics of the system. The RG analysis does not give information about the stability. It finds the frequency with elevated interactions. If we want to see that if that interactions are capable of making the system unstable, we can move to grayish-green circle analysis. In this analysis, there are circles which are superimposed on the Nyquist diagram of 4 control loops. The larger the diameter, the higher interactions between control loops. So again, this is the result is similar to the RGA here, 300 to 400 radian. It is the elevated interactions, the frequency band. But as it is observable, the DC voltage, these grayish-green bands are encircling the -1. This is Nyquist plot. So grayish-green bands are encircling -1 in DC voltage, the total energy 1, and total energy 2, only total energy 2 and DC voltage. This means that the interactions are capable of making system unstable if a designer does not taking care of them. However, with regard to the active power and the total energy 1, the Grishko circle, they do not encircle -1, so they are safer. And last, the interaction between all inputs and all outputs. The tools is singular value decomposition HVD. So as it is shown here, if the inputs have this direction, which means that if the DC voltage drops by minus 10%, power is increased by 5% or so, total energy is changing by 80%, which is a bit unrealistic. And if this combination of input and output with this magnitude and also direction, minus or positive, if this happens, 1 per unit drop we should expect on the DC voltage. And the other outputs are not much affected. So this gives information about that if what is the worst condition considering all inputs and all outputs that I expect to see in my system. So if this input direction happens at the same time, I expect that my DC voltage drops -1 per unit. It means that I cannot have control over my DC voltage, and DC voltage would goes from nominal value to 0. It is -1 per unit drop. This is not realistic because I mean the analysis is giving some maybe mathematical information, but to have this input vector happens, it is very rare. I mean the possibility of having this input vector is not much. However, a designer would know that what is the worst condition. Maybe in another system there is a combination, input combination, which is very probable, and then the output vector, critical output vector situation would be important. And with all this information we can tune our control system in a better way. Usually when a designer is controlling her control system, the main factors commonly are settling time, overshoot, undershoot, overall stability of the system. Those are important factors indeed, but usually the interactions are not an influential parameters. In this study, we are suggesting that interactions could be very crucial parameter. For example, PI controller of DC voltage, we are doing a sweep from 0.1 to 10. I mean both proportional and integral is multiplied by 0.1 to 10. And as we go through these two values and we plot all the RGA values, which shows the level of interactions from these 4 control references and 2 only DC voltage, we can see there is 2 specific region with an elevated interactions. So if we are not careful with the tuning, then it is possible that we fall into one of these region which cause very high interaction level. So maybe the situation is fine with other parameters, but the interactions is not in an optimal situation. So interaction is also an important factor to be considered during the design. For example, in our case study, when the PI gain is multiplied by 0.55, this is the RJ values, and there is no peak in and the peak is minimal if it is like a valley, and this is the region of high interaction. This is super high interaction, but this green line is related to the PI gain of 0.55, and at this gain, the interactions are not significant, but a designer usually should find a compromise between settling time, overall stability, and interactions level, and to go for the most optimal and most suitable for the specific system she's designing. So to wrap up, we try to classify the interaction in VSC HVDC system based on the nature of interaction, which could be state variable interactions and input-output interactions. The input-output interactions we divided into three types based on is it single input, single output, multiple input, multiple input output, which is about the coupling between control system, and type 3, which is the considering all the input and all the output all together. The decision on which input and outputs, it all depends on the design and the system. For each class of interaction, a tool was suggested which is capable of studying the interactions. It was eigenvalue, to just name a few, was eigenvalue, participation factor, Bode plot, normalized input participation, SVD analyzers, RGA analyzers, Gersh scoring circles, and I guess that was it. Yeah. And at the end, we have a case to show that how this study of interactions can be utilized in the control system design. Thanks for your attention. Hope you all have a nice day.